Any general questions, problems, anything? I'm under 300 papers left to grade, so I'm still hoping to get that wrapped up by the weekend. And I did post project 2, so it is virtually impossible for you to do this in the hour before it's due. So please, please, please look at it sooner rather than later. And do remember, the projects are replacements for exams. The expectation is that you demonstrate significant chemical knowledge. It is not essentially the equivalent of the sprint reflections, which just ask you for a quick reflection. So you need to find some good science to explain, in this case, the kinetics of your chosen reaction or reaction sequence. Any general questions on that? Okay, we were talking about assumptions. And again, we did this quickly at the end Wednesday, so just to back up and reemphasize it. My general strategy is, quite frankly, to always try simplify an assumption. Right? There are ways you could guess ahead of time whether it's likely to work or not. Right? Quite frankly, looking at this problem, I knew it wouldn't work before I started. Right? But as I'm fond of saying, it takes longer to decide whether it's a good idea to try the assumption than it does to actually try it and have it fail. Right? And so, right, I don't need to try to calculate or estimate whether or not the assumption is likely to be a good idea, because I do have a test for the assumption after the fact, and it does take very little time to calculate X here once I make the assumption, right? So if I assume X is less than 0.0025, both X's in the denominator are insignificant in my assumption relative to the number I'm comparing them to. And so since they are insignificant, they disappear. And I just cross multiply, divide by 4, take the square root, and I get technically plus or minus 0.013, right? And again, my 5% rule says that my standard for small is 5% of the number I'm comparing it to. And so, you know, multiply by 0.05 or divide by 20, however you'd like to look at it. And so from the moment I made the assumption, my standard for small was 0.0025 divided by 20, 5% of 0.0025. So my assumption immediately leads to the standard for small being 0.000125, right? And so any number greater than that is not small. Any number smaller than that is small, right? Again, it is a somewhat arbitrary standard designed to leave me with 2 sig figs, right? If I need 3 sig figs, I wouldn't do this, right? I would have to use a 0.5% rule. If I only needed 1 sig fig, right, I probably have a more of a 10 or 20% rule, right? But in this case, and in general, I have my 2 sig fig rule. So in this case, it fails. If it fails, I have to come up with another way to solve my equation. In this case, it is a quadratic if I multiply it out, so I could use the quadratic formula. Since we really don't have any tests where you don't have access to the internet or a graphing calculator, quite frankly, there's any number of ways you could solve this. Really, my quadratic promise is more based around having more traditional testing where you may not have access to the internet And as we mentioned, on Wednesday, there are websites and other internet resources that will allow you to solve even higher order polynomial equations. Right. Right. Whenever I have a higher order polynomial equation, meaning 2 or higher, there are multiple roots, right? For a polynomial equation, there's always as many roots as you have powers of x. So for a quadratic, there's always 2 roots, right? And again, mathematically, there is no distinction, right? I don't really care what those roots are, right? In fact, if you've done any fancier math, you can even have imaginary roots, right? Mathematically, there's no distinction that would make both of those roots are equally valid in a strictly mathematical sense, right? But, and this is the case 99.99% of the time, there is only one solution to my equilibrium problem. And what really defines it is not anything about the math, it's what happens when you turn the math back into the chemistry, right? X is the solution to a polynomial equation, right? X is also supposed to be the solution to the ice chart, right? And so it has to make chemical sense, right? And only one of the roots does, right? Since my equilibrium amounts are 0.0025 minus X for the hydrogen and 0.005 minus X for the iodine, if I use the larger of the 2 roots I found, both of those numbers are going to be negative, right? And that makes no physical sense. You cannot have negative moles. You cannot have negative grams. If you can find a way to do it, let me know. We'll all be rich, because the first thing we're going to do is owe the universe 1,000 kilograms of gold. And so I reject that root, not because of any mathematical reason, but strictly because it does not make chemical sense. X can't be 0.005736. X can, however, be 0.002356. And so again, I put it back in the ice chart. It gives me all of my equilibrium concentrations. That's what I was looking for, and I have an answer. Right. It's worth noting, this last step should always be done, right? A lot of times it seems like my whole goal is to get X, and a lot of times it is, and so people go this far and maybe circle the answer. In principle, the answer might not be X at all, depending on what the question is. The answer is somewhere in the ice chart, right? And so my last step should always be putting the X value back into the ice chart, right? If the question was how much hydrogen is left, the answer is not 0.002356. In fact, none of the answers is 0.002356, right? That's the X that solves the problem, but my equilibrium concentrations are all related to X, but none of them are X, right? And so my last step really in any equilibrium problem is the ice chart, right? And so in my usual fashion, in spinning large letters, right, you always want to go the extra step, because there's no reason why X itself has to be the answer, right? All of my energy was dedicated to finding X, but that was just because X made the ice chart complete. X itself was not what I was looking for. Yes, no, maybe. Zoom homies, are we good? We cool? I will leave out pigeon jokes. Okay, the one other little equilibrium problem. All right, calcium carbonate will decompose to give calcium oxide and carbon dioxide. True story. Calcium carbonate, better known as, anybody know? calcium carbonate is also better known as. It is in eggshells. It's also, anybody know? Chalk. It's also probably Tums, calcium and or magnesium carbonate, but also, very importantly, where's my environmental science people? Limestone. Calcium carbonate is actually limestone. In nature, we'll see it again in a week or so. It's actually very important as a natural buffer for water systems in nature. But calcium carbonate will decompose at elevated temperatures, right? So I put a sample of calcium carbonate in an otherwise evacuated 1 liter flask and heated to 350 degrees C. Why evacuated? Or what do I mean by evacuated? It's in a vacuum, meaning specifically in less scientific sounding words, it's empty, and very specifically, there's no air. There's no air in it. Because again, if you read ahead, right, this is a KP problem, pressure is an issue. All gases exert pressure, not just the ones you care about, right? And so, as I'm fond of saying when we talk about gas laws, you're always measuring the total pressure, right? If I stick a pressure gauge on my flask, it's going to tell me the total pressure, which would include any air that was in there before the reaction even started, right? And so it matters in terms of what I'm measuring, whether or not there's air, even though the air itself is not doing anything, right? So sometimes I evacuate my flask because I don't want the air to interfere. If I have a reaction, for example, that's oxygen sensitive, I don't want any oxygen in there, and so I might evacuate it, or I might purge it with something other than oxygen, right? But from a pressure measurement standpoint, right, in this case, carbon dioxide is my product. If I'm going to measure my product, and I am, right, the measurement I'm going to get is actually not the pressure of carbon dioxide, it's the pressure of all gases in the system. And so if I started with 1 atmosphere of air, right, what I'm going to measure is 1 atmosphere of air plus the pressure of the gas carbon dioxide from the reaction. If I evacuate the flask, there is no air pressure and I'm only measuring the pressure of carbon dioxide. In this case, I could do it either way because it's not that my reaction is air sensitive, but it does matter in terms of how I interpret the measured pressure, right? Measured pressures are always total pressure. And so I have to take account of all gases, even if I don't care about them, right? And in this case, I wouldn't care about any background air pressure, probably, right? But it would affect how I interpret the measurement, which, if you read ahead, is that when I reached equilibrium, the total pressure in the flask was 0.105 atmosphere. That is always going to be the pressure of all gases. All right. And so it asks me to find Kc and Kp. It uses the E word. There's a capital K there. I'm immediately thinking equilibrium. And of course, all equilibrium problems, they have 3 parts. This one's no different, right? And so balanced equation is always my first and most important part because, after all, my ice chart and my equilibrium expression descend directly from the balanced equation, so I can't really do anything until I have my balanced equation. The first sentence of my problem essentially stated in words the balanced equation. Calcium carbonate will decompose to calcium oxide, which is a solid, as most ionic compounds are, at moderate temperatures, and good old carbon dioxide, everyone's frenemy these days when it comes to gases. All right, and once I've done that, I can immediately write the equilibrium constant expression and construct my ice chart. In this case, welcome to the simplest equilibrium expression of the semester, right? I have two solids and a gas, right? So again, pure solids and pure liquids don't really have concentration. They definitely don't have pressure. So they are taken to have a constant activity of 1, meaning they essentially do not appear in my equilibrium expression. So in fact, the Kc value is simply the concentration of carbon dioxide, right? And the Kp is simply the pressure of carbon dioxide. Right. And so I was told that a sample of calcium carbonate was put in a flask, but I was not told how much, right? That is not really a defect in this case, because when I construct the ice chart, how much doesn't matter, right? In the sense that, right, my ice chart, let me fit it under here, right? These don't need to be tracked at all because they don't appear here. The only thing I really need to care about is the carbon dioxide, because it's only the carbon dioxide that actually feeds into the equilibrium expression. Now, I need to have enough calcium carbonate to get to equilibrium, right? Although that is not the point of my particular problem here. But how much calcium carbonate I have is somewhat irrelevant, right? As long as I have a minimal amount to get to equilibrium. And so, you know, I already have my answer. Since it was an evacuated flask, the total pressure is carbon dioxide and carbon dioxide alone. The only thing that matters to my Kc or my Kp is the amount of carbon dioxide, right? And so it's just a matter of getting my units right. For Kc, I need moles per liter, I need molarity, right? That is fundamentally a gas law problem, right? It is most common by a lot to measure the pressure of gases. They are incredibly difficult to weigh accurately. All right. Volume can be measured, but only in tandem with pressure. So it is sometimes partial volumes that get measured. We talked about this with when we talked about gas laws in the fall. It's really a question of containment, by which I mean if you have a hard-walled flask, you usually measure pressure because the volume doesn't change. And so increasing the amount of a gas increases the pressure because the volume can't change. If you're in a balloon, right, the volume changes, but the pressure is always atmospheric pressure, right? And so if you do this reaction or any gas phase process in a balloon, it's more common to measure volume than pressure. If you do the reaction in a hard-walled flask, right, it is more common to measure pressure because the volume can't change, right? Of course, in the context of my gas law, I really need to know PV and T, right? Because what the ideal gas law really is doing is essentially striking a balance between the 4 variables that matter for a gas, right? The pressure, volume, moles, and temperature are all interrelated, right? If you don't like the ideal gas law because you feel your gas is not ideal, right, you can use the van der Waal equation or one of the non-ideal gas expressions, right? That makes the algebra a little different. And you need to know a few more things, like sometimes the volume of the molecules, right? But in general, some gas law will allow me to calculate moles from pressure, right, and volume. And so for us, since we're dealing in moderate pressures and not generally extreme pressures. We're going to use the ideal gas law. And so, right, if I want molarity, right, that's really N over V, moles per liter, I sometimes refer to this as really a pseudomolarity, in the sense that it's not a molarity exactly in the same way you think of it for a solution, right, where it's kind of a solute-solvent issue, right? But it is a molarity in the sense that it's describing the moles per liter of space. And so it is a concentration. And so I had the pressure in this case, which was 0.105. So P over RT gives me the molarity. All right. This is our old gas law R, because liters and atmospheres are my units. Right? Not my joules R, because I don't have joules here. And of course, remember, right, pressure, like energy, requires that I have temperature measured in absolute temperature scale, because I need the pressure to go to zero when the temperature goes to zero. And I don't want the pressure to go to zero when it happens to be cold outside. Otherwise, we would all suffocate. Right? If the pressure outside went to zero at 0 degrees Celsius, there would be no air to breathe. Right? If you need any proof that Celsius won't work here, right? And so I get a molarity for my gas, and again, sadly, there's no fancy math to do here, since the Kc depended only on the molarity of the carbon dioxide. Right? Kp was really even easier because I was given the pressure up front. Right? The pressure, the total pressure in the flask was 0.105 atmospheres. The only gas in the flask is the carbon dioxide, because I evacuated before I started. And so I actually knew Kp before I did anything. Right? And this problem, kind of boring, really. Didn't have any fancy exponents. Honestly, didn't even really need an ice chart. How disappointing. Right? I only bring it up because it is the general relationship between Kc and Kp on display in a relatively simple problem, right? Because here it is, right? My Kc depends on molarity, which is N over V, right? My Kp depends on pressure. They're directly related through my gas law. In fact, the only difference between my pressure and my molarity is RT. Right. And of course, R is the gas constant. I know that. T I also have to always know for an equilibrium, because equilibria are temperature dependent. Right. And so it is very straightforward to go back and forth between Kp and Kc. Right. Please note, it looks like in this problem, because there's only one gas, but Kp itself is not a pressure. Right? Kp is a combination of pressures. In this case, it just so happens there's only one gas. Right? And so if I want to go back and forth between my Kp and my Kc picture, all I need is the RTs. Right? And in fact, that allows me to actually go directly from Kp to Kc. Right? In this case, the only difference is RT. Even in a more complicated gas phase reaction, I'm just going to need more RTs, because every pressure, right, is related to every concentration by an RT. Right? You may hate this, but I don't hold you responsible for derivations. But here it is. If you speak algebra and, like to speak algebra, right? If I took a generic gas phase reaction that had multiple gases, right, my Kc and Kp are a combination of all of the gases present, right? And so in the case of the KC, it's just molarities raised to their stoichiometry. In the case of KP, it's just the pressures raised to their stoichiometry. Again, all pressures are related to all molarities by good old RT, right? In fact, there's really a KP hiding in my KC, right? Again, most frequently I measure pressures for gases. And so typically what I would know up front in this problem is the pressure, not the molarity. And so if I wanted, like in the last problem, to calculate Kc, I have to get the molarity from the pressure. How? Pressure divided by RT, right? But what I really have is a whole bunch of RT terms that I could take out, right? And if I take them out, there's good old Kp, right? And so as you can see in somewhat exotic algebraic fashion, right, every Kc value for a reaction is related to the Kp value for the reaction directly. I just have to deal with all the RTs. Right. And so if I combine them all, right, what I really have is a difference in stoichiometry, right? If you think in terms of the balanced equation, Z is the stoichiometry of the products, X and Y were the stoichiometry of the reactants, right? The number of RTs I need is the difference in the total stoichiometric coefficients of the products and reactants. And so the way this generally gets written, right, is as a delta N, right? Please note, this is another one of those cases where it is somewhat deceptive, right? It's not really a difference in moles, right? Even though it's written as delta moles, right? It's a difference in stoichiometry, right? So it's not that I had 0.1 moles of products and 0.2 moles of reactants, and so 0.1 minus 0.2 is negative 0.1, right? My delta N comes directly from the balanced equation, right? And so here's a reaction with stoichiometry, right? I have a Kp. I don't have to do much fancy to go to Kc other than to convert Kp directly to Kc, the conversion being really just RTs, right? And so if I look at my balanced equation, there's a total of 2 plus 1, right? There's 3 stoichiometric moles of products. There's 2 stoichiometric moles of reactants. I need 3 minus 2 RTs, right? And so I don't need any specific quantities or moles, even if this is part of a bigger problem that has specific moles of reactants and products. That's irrelevant to my Kp to Kc conversion, right? Delta N represents stoichiometry, not actual measured moles of stuff, right? And it's always products minus reactants. So I had 3 moles of products minus 2 moles of reactants, right, which is 1. And so I just need 1 over RT conversion factor to go from Kc to Kp. And of course, you could go the other way. The math just is the reverse, where I would know Kp and I'm trying to calculate, or I know Kc and I'm trying to calculate Kp. We don't do a lot of this from this point forward because we mostly deal in aqueous reactions. And so as soon as the reaction is aqueous, even if one of the products was a gas, there's really no Kp, right? The only time there's ever a Kp is if you have a completely gas phase reaction, or as we saw with my calcium carbonate, if it's pure solids and pure liquids with just gases. As soon as I have aqueous species, right, there is only a Kc and technically a Keq. I cannot define what a KP means for an aqueous reaction because solutions don't have pressure. Right. But there are gas phase reactions, right? I mean, notably the Haber process, which pops up every now and then, and here it is again, right? People have made the case, and I think you could make the case that the Haber process, which is an all gas phase reaction, is the most important reaction in the history of mankind. Right? Because ammonia allowed for the production of commercial fertilizers, which allowed for a huge increase in crop yields, which really fueled the Industrial Revolution. Right? Prior to the Haber process, somewhere around 80% of the population was dedicated to generating food. Right? After the Haber process, right, less than 10% ultimately of the population was dedicated to creating food, which freed up the other 90% for the Industrial Revolution. So, but that's a strictly gas phase reaction, so it has a Kc and a Kp. But starting this moment, we see very few gases because we're all about the aqueous reactions in here. And really, I would argue, if you have truly understood equilibrium at this point, you should be blissfully bored for the next 4 weeks or so, because nothing really changes. All equilibrium problems, after all, have 3 parts, and so we're going to do the same thing for every single equilibrium problem, right? The only difference is, right, that we're now applying them to specific reaction types. That doesn't really change anything, right? The only reason they even get talked about separately is not because anything fundamentally different happens, right? It's still an equilibrium. It still has 3 parts, which means I still solve everything: balanced equation, equilibrium expression, ice chart, solve, right? But each of the reaction types we talk about does have sort of a special feature all its own. It doesn't change the way I solve it, right? But it does sometimes change the way I report it, which is the case for our first reaction type, which are acids and bases. Right. And so, you know, I started equilibrium by saying K is K is K is K. You know how much I like to repeat myself in the hopes that you hear me at least one of those times, right? It's really all about the subscripts, not changing anything fundamental about K, but telling me something about the reaction, right? Kc and Kp, right? We're all about the units, right? The next 3 are all about acids and bases. A is for acid, technically acid dissociation. I hate that word. We'll talk more about my hate in a minute. B is for bases. Again, technically base dissociation. Hate that word. And W is really for water. Right? It's really just trying to tell me what the specific reaction is that the equilibrium constant belongs to. It doesn't change anything about how I'm going to solve it, because after all, K is K is K is K. Right? And so I remind you of what we talked about in the fall, and then I will admonish you to forget everything you were told in high school about this. I have been known, if there were more people in the room, I would stand up on the front desk and yell again, but there's so few of you and you're clustered around the front desk that just seems intimidating, right? The simplifications you're taught in high school are the enemy of your learning here, for a reason I will show you in a minute, right? We are talking about Bronsted-Lowry acids, right? And these have a very specific, very narrow definition, right? A Bronsted-Lowry acid is a proton donor, period. If it donates a proton, it's a Bronsted-Lowry acid. If it's a Bronsted-Lowry acid, it must be donating a proton. There is no wiggle room here, right? That is strictly definitional, right? Unsurprisingly, perhaps, right, a Bronsted-Lowry base is a proton acceptor. This is why they go together. Because frankly, what does it mean to donate a proton if nobody accepts it? Right? I mean, it'd be great. I could be the world's greatest philanthropist. I will donate $1 trillion right now as long as nobody accepts it. Right? And so this is why acids and bases always go together. Because if I'm going to donate a proton, somebody has to take it. And if somebody takes it, that entity that takes it is automatically a base. And so, chemically speaking, if you have an acid being an acid, as opposed to being a breakfast drink, I mean, orange juice is an acid, right? But if the acid is really being an acid, it's donating a proton, which means there must be a base there accepting it. Right? Most of you have been horribly twisted and misguided by high school on this point, because get ready to unmute, right? Because you are frequently taught that when an acid reacts with a base, you get a salt and water. It's a damn lie. It is 100% untrue. It is sometimes true by accident. It is not true. Because it's embedded in the definition, right? The only thing that actually happens when an acid meets a base is that a proton gets transferred. There is nothing about that proton transfer that guarantees I get a salt at all, much less water. In fact, dare I say, 99% of acid-base reactions do not involve either a salt or water. Right? For example, right, HCl is an acid, NH3 is a base. The product, right, if I transfer the proton from the acid to the base, is Cl minus and NH4 plus. Where's the frickin' water? There isn't any, nor should there be, despite the lies you were told in high school. And I'm telling you, this is a pernicious, again, technically oversimplification, right? There are times when that does happen, right? But those are in some sense are special cases. And this really, really, really gets in the way of what really should be a simple concept, right? Because if I have an acid and a base, as soon as I see an acid, I'm going to move a proton over. And I get what I get. I didn't have to think very hard about that. I took the H off the HCl. That left me Cl minus. No matter what I thought I was going to get, wanted to get, right? Take the H off, that's all I got left. If I put it on the NH3, I now got 4 with a plus charge because it's an H plus. And I get what I get. Yet, people will twist themselves into knots trying to get a salt and water. I literally, for this reaction, once on a final exam, got this. You laugh, it could be you. Well, not you, it's the person next to you. Look at them and scoff. Because it is so ingrained that you have to get a salt and a water. She made one. Even though there's no oxygen on the left, and somehow the nitrogen became a sodium. I mean, it's only add an A, right? But now I have a salt and water, I feel better about it, right? And it shouldn't even require that much thought, because again, as soon as I go, hey, it's an acid and a base, I move the proton over, I get what I get. Right? Okay? And so the trick here if there is one, is to recognize that it's an acid-base reaction. As soon as I recognize that, the products are, you're never supposed to say this, but I will, are obvious. Because the only thing by definition that can possibly happen if I have an acid and a base is that a proton moves over. This requires very little thinking. The more you're thinking, right, the less you understand about acids and bases, because the only thing that ever happens when an acid meets a base is a proton goes from the acid to the base, period. The products are whatever they are, usually not water, and usually not a salt. All right. In fact, the most common acid is water. Right? It may not be obvious if I write it as good old dihydrogen monoxide. Right? If I write it as hydrogen hydroxide, it's maybe a little more obvious because there's really two pieces to my water. There's a hydroxide, which is one of our polyatomic ions, and there's an H plus stuck to it. Right? And so the H plus actually can be donated. Right? Of course, water is also probably the most common base because it does have a hydroxide in it. It's hydrogen hydroxide. Not that bases have to have hydroxides. Right. But hydroxide is one of those species that when it pops up can be basic because fundamentally, right, what makes an acid and a base is fundamentally structural. Right. Water is not the only compound that does this, so there's a name for it. They are called amphoteric, and sometimes, confusingly, they're also called amphiprotic. Those are two very technical, foreign-sounding words that both mean the same thing, right? Meaning it can act as either an acid or a base, right? The protic part, of course, referring to whether it's accepting or donating a proton, because that is our definition. Right. The reason I bring this up is because what that means is as soon as I have an aqueous solution, because of course aqueous means water, I have an acid. And I also have a base because water is both. Right. And so in some sense, the whole point in discussing these acid-base reactions is not because of the acids and bases like HCl and NH3, which I just had. In fact, it'll be a good week probably before we see that again. All right. It's because as soon as I have an aqueous solution, I have an acid-base reaction. Because the water can be an acid and the water can be a base. Which one it decides to be depends on what you put in it, because it's not very good at either. All right. And so we actually have the situation where the simplest acid-base solutions have chemistry going on in them because of, interestingly, the solvent. Right? HCl is an acid. If I put HCl in water, right, I have an acid-base reaction even before I've added a base, right? If I'm trying to do an acid-base chemistry, I probably have an acid of choice and a base by choice. But if I choose to do my reaction in water, there's an acid-base reaction going on with the solvent. All right. Oh, where does the time go? Right. So one of the reasons we discussed this as a separate special topic, because again, it's just an equilibrium problem. All equilibrium problems still have. So I'm not doing anything different, right? But what I do have is the kind of unusual situation where the solvent does a reaction all on its own, even if it's not my primary interest, right? If I want to mix HCl and NH3, which I just did a minute ago, but I want to do it in water, the HCl will react with the water and the NH3 will react with the water as well as reacting with each other, right? And so, as I mentioned before, part of the reason we discuss these as separate topics is because they each have this special feature to it, right? And so my aqueous acids and bases have the kind of unique feature that the solvent suddenly becomes a reactant, right? They also have another little special feature, which is that rather than reporting the molarity, right, it is more common to report the pH, right? Which is really just a backwards way of specifying the molarity, right? Please note, pH also is narrowly defined, right? pH is really molarity, right? First of all, right, it's a log scale for molarity, but more importantly, it is only the molarity of the donated protons in a water solution. It is not the concentration of the acid. It is not the concentration of the base. It is very narrowly defined as the concentration of the donated protons, right, which were donated to the water, right? And so the pH is either the negative log of the H plus, which is really a somewhat fictional species in an aqueous solution because the H plus is really stuck to a water. And so by definition, really the pH is the negative log of hydronium, which is my donated proton from the acid to water, right? It is the only thing I can identify with a pH. I cannot talk about the concentration of HCl as a pH, right? pH is only the concentration of the hydronium, but because of my good old special feature that all of a sudden, if I'm in an aqueous solution, the water plays a role. If I throw HCl, which is an acid, into water, right, whether I want it or not, the HCl will react with the water. Can't help it. Because water is a base. Not a good one, right? HCl is a much better acid than water is a base. But if I throw HCl in water, those are the only two things in the beaker, right? So no matter how reluctantly a base the water might be, it's actually the best base in the beaker. And the good news for our reaction in this case, HCl is a really good acid for reasons we'll have to talk about on Monday, right? And so as soon as I throw my acid in the water, again, even if I'm trying to react my HCl with something else, right, the HCl will donate protons to the water because water is a base. And so that makes hydronium. And so you can talk about the concentration here in terms of the hydronium concentration, which is what the pH is trying to identify. Right. The concentration of the HCl itself has to be specified the old-fashioned way with something like molarity, right? But if I put it in water, right, there's technically an ice chart here. There's technically an equilibrium problem there. That is our whole focus really for next week, right? But because of that, I can talk about pH, which is really the equilibrium amount of hydronium. And since I really have no time left, I will leave it there for now. Next week, all about acids and bases, and fundamentally water, because everything's aqueous. Have a good weekend. We should have, pray for me, all of the projects graded by the end of the weekend. And please, please, please do look at Project 2.
Professor, do you have a Great Pyrenees?
I used to, but he's passed away, but yes.
Oh, he's so cute. I have one too. He looks just like your picture.
Oh, I love the Piers. I mean, I currently have like virtually the opposite. Well, not quite the opposite, I suppose. Like something tiny would be the opposite, but I have Newfoundlands now.
Oh, my best friend in high school had Newfoundlands. They're similar.
Well, they look similar, but like personality-wise, they're virtually the opposite. Like
Yeah.
my Newfoundlands do not even like understand aggression. Like, you know, they'll go up to a fence and the dog will be like barking like crazy because they don't want him near their yard. And my dogs just stand there wagging their tail like, oh, he wants to play, right?
All mine does is bark. Yeah, they're definitely barking.
Well, and the Piers, though, I mean, because they're a guard breed,
Yeah.
right? I mean, they're less friendly, especially with other dogs.
Yeah.
But I always thought they made a good pair because Kira, my old girl, I got her as a companion for the Pier because she was just so passive, she wasn't going to fight with him. And he really quickly adopted her and decided to become her guardian. But like we would go to the park, and for some reason, dogs that are all aggressive like to attack the Newfoundlands. I think because, well, I think, and again, small dogs will sometimes attack my Newfoundlands. but again, I think it's because the Newfoundlands are just so passive, you know what I mean?
Mhm.
So it's just like dog bullying, right? And so, but that would never, and Kira just didn't get it, my Newf, right? The dog would be snarling and she's wagging her tail and the dog's got a piece of, well, it's got a mouthful of fur because, you know, and she's just not getting it. But like when Willie was alive, you know, you didn't mess with Kira. He would just go over, take his paw, flip the dog on his back, and just stand on him. You know,
that's how they are for sure. Yeah, we had a golden when I was a kid, like our family dog, and he was that way. He was so passive, and now my Great Pyrenees, Sharky, his name's Sharky. Based off his personality, he's like a shark. I mean, he's always barking. Yeah, he definitely has some aggression with other dogs. We adopted him though, so I don't know what he went through before.
Yeah, because especially when I'd be in the park and everybody's like, because of course, big fluffy white dog, everybody wanted one. And I know it, and I always felt I was doing a service to the public to say, look, you don't want them as a family dog, you know, unless you're good with dogs, because especially not that they will go after the family.
Yeah.
But they're big, and so if you have like small kids and your Pyrenees, you know, just charges the fence, it'll knock the kid over. And it's just really hard to take them to parks and stuff where there might be other dogs because it's really weird. I mean, I find dog genetics to be interesting anyway, but especially with the Piers because and the Noofs, I mean, it's like in them. So here's a Pier, right? And of course, all dogs are like wolf descendants.
Yeah.
But here's the dog, the Pier, who interprets other dogs to be wolves and therefore a threat.
Yeah.
You know, and it's weird. It's like, don't you recognize that's a dog? Right?
Yeah, I know.
And on the other hand, the weirdest thing about the Newfoundlands is they instinctively like small children. I'm like, what kind of wolf characteristic is that? Right? Why is there a gene for liking human children? Right. But that's why they were an interesting combination. And you're right, they look very similar, but personality-wise, they were almost like the opposite.
Yeah, Pyrenees they're tough. Mine's super stubborn. He does not listen. He has no recall. Like he doesn't know his name when he's like busy.
Well, no, I mean it's funny when he was a puppy, we took Willie to a dog trainer, and the first meeting had no dogs for puppies, right? It was just the owners, and you know, so he went around and said, "What kind of dog do you have?" and whatever. And so I said Pyrenees, and he said, "Oh," and I said, "Why?" He goes, and this is, again, it's a breeding thing. You know, like German Shepherds were guard dogs, but they worked with a shepherd. And so it was always the dog and the human. If you
Right.
look at the way they use Pyrenees, they send them out in the mountains by themselves.
Uh-huh.
So by breeding, they have to decide on their own. So they don't like to listen. Right? And the way the dog trainer put it, he said, look, he goes, you got a Pyrenees? He goes, you tell him to do something. I go, he'll do it once. I go, you tell him to do it again. He'll look at you funny, like, why are you asking me? He goes, you tell him to do it a third time, he'll just stand there and flip you off. Right?
It's so true. I'm like, come on, come on. He just looks at me and then looks away like he can't hear me.
Well, he wants to think for himself.
Yeah.
It's really interesting. And I mean, one of the best Pier story, and I do miss my Pier. I almost got another one after he died, but then my Noof was so lonely, I just had to get first dog available, which happened to be another Noof.
Yeah.
Because I didn't want a small dog because I just worry about them accidentally stepping on them. I mean, when you got a 140-pound dog, you can't put a 30-pound dog with it.
No,
Bad things happen. But anyway, so when it was a couple of years ago with the California wildfires, and this family had to abandon the farm, and they could not get the dog to go with them because the dog wanted to stay with the goats. But the fire was coming, so the family left, you know, and they were sure that they lost everything, dog, goats, whatever, right? They get back to the farm. Not only are all the goats there, a little singed, and the dog's there, but he also had adopted a baby doe, right?
What?
Well, because Piers love just animals other than dogs. I mean, it's another one of those weird things. And so the fire came through, and that dog, you know, protected his flock and somehow managed to pick up a stray doe in the process and managed to apparently get them into a stream bed.
Oh my gosh, that's crazy.
Yeah, and again, it's all breed. It's not like he was trained for wildfires.
Right.
You know? I mean, they're just absolutely amazing what's in their breeding, you know. But as a result, I always felt bad that I didn't get Willie a goat or something. Not that I'm zoned for goats, because I think he just really needed somebody to protect. Which is why when Kira came along, even though he was suspicious of dogs, he just kind of adopted her as his, you know, object of protection.
Yeah, I think like he's kind of done that with my boyfriend and I. We lived together, and he never was aggressive with dogs when we first got him. So he's like between 4 and 6 years old when we just got him a couple of months ago when we got him from the shelter, and he had no aggression with dogs. He was great. Like he'd, you know, hang out outside with them, whatever at the shelter. But since we've been getting closer, he's been getting like more aggressive. So I think he's kind of taken us, like when we go on walks and stuff, he'll get really aggressive with other dogs. I think he starts
How
to think
old is he?
What'd you say?
How old?
Between 4 and 6. They don't know because they got him from the street.
Yeah, I mean with Willie, we went to the park from when he was a tiny puppy, and it's well known they get to be about 18 months old or so, and that's when they, you know, really start to shove other dogs away. And so after that, it was really hard for me to mix them. But 4 to 6, he should have. I don't know. I mean, partly I guess it's what they're used to. But they generally, that's why they don't do well in kennels, because of all the other dogs around.
Right.
Yeah, I mean, I miss my Pier, although the Noofs are so much easier. But I really felt like, I mean, after he died, like Kira, the same dog kept attacking her in the park. And that dog didn't dare touch her when Willie was around. Because one time he tried, Willie flipped the dog over, and it was a pit bull. But he took him with his paw, he flipped him over, and he just stood in him. I mean, he didn't bite him or anything, but he just stood on him, and he was not going to let him mess with Kira. But then after he died, that dog, every time he would see Kira, he would break away from the owner and grab a mouthful of fur. And Kira never did seem to quite understand it. But so they kind of make a nice pair, such as they are, mismatched pair that they are.
Yeah, I think if I were to do it again, I would probably get one younger and work with another dog. But he's a good boy.
I don't know. I think they just kind of, I think they just kind of need a job. That's why, I don't think they're like good apartment dogs. I don't even think they're necessarily good family dogs if you have small children, you know, adults, because again, they will, but like my parents, I accidentally got this dog because we were getting a dog for my parents. And so my parents had his brother, and they grew up together. And so they played together constantly. When they got to be like 18 months old, Willie's brother would not let him anywhere near the house.
Really?
They couldn't mix them together, and they were together from like birth until 18 months. But all of a sudden, that was his house. He was an adult, and the dog was a threat. And so we couldn't let them play together anymore after they were about 18 months old. And then it got to where the dog basically adopted my mother,
Mm-hmm.
and he wouldn't let my father near my mother at times.
Oh no.
So somehow that my father, I mean, I partly blame my father for that. He was not very assertive with the dog, right?
Yeah.
But yeah, he basically adopted my mother and protected my mother from my father. Even though one time my father figured, oh,